Okay, so basically we start from where we left last time. So the general topic, which basically constitute the subject that we are trying to see in this part of the course, is the finite element formulation associated with the study of a system of multiple bodies, with particular regard to the capability of these formulations to correctly represent the dynamics of these systems, in particular with the apparently, let's say, mandatory feature to be able to converge when applied within this particular field that we have described, which are the finite element formulations. In particular, what we have seen is that when we describe these element types, we can carry out this description within various formulations. And these various formulations mainly differ with respect to the, let's say, frame of reference, which we adopt to describe the nodal coordinates. We have formulated two different element types in the so-called absolute nodal formulation, in which the element frame of reference is the inertial frame. And in so doing, we have carried out the description of the 2D rectangular isoparametric element and 1D non-isoparametric element. Now, what we have to ascertain is whether these two elements actually satisfy the requirements of convergence when used. Meaning that, of course, when you discretize, because this is what we actually do when we implement this restricted formulation to continuous body, we are basically discretizing a continuum. Well, when we discretize and we apply this formulation, we eventually approach a convergence, which can be of different form, but it has to be granted, okay, for this formulation. Well, in order to be able to, let's say, achieve this convergence, we need to satisfy two main requirements. The first requirement is continuity, okay, as we were already anticipating last time, meaning that basically you have to have no issues regarding possible openings due to tearing, which happen inside your domain. So whatever point you take within your domain, there must be a path which links the 2 points completely contained within your body. This is basically the hypothesis of basic connectivity or continuity. Okay, why is it that? So if you think about it, because I mean, this, let's say, take into account one of the questions that one of your colleagues made after the lecture last time. So when you let's actually recap a little bit the frame in which we are working. So we have the dynamical equations of motion, okay, that we have already learned how to, to write and to solve. When you solve these equations of motion, what you get is the solution at the so-called nodes. So the generalized quantities, the generalized coordinates that you, that basically, the generalized quantities, the generalized coordinates that form the unknowns of your equations, in these restricted formulations, in this finite element formulation in particular that we are describing, are represented by the nodal coordinates. Okay, so solving the equations of motion means getting your nodal coordinates. Okay, now with your finite element approach, which is a particular case of your restricted formulation, you are able to reconstruct the solution of the problem, from the nodes to the overall quantity, to the overall domain, okay, to the whole, let's say, continuum, which constitute your different bodies. Okay, now, when you do so, basically you have a system of forces and actions in general, so forces and moments, okay? When you solve this equation, you basically get what? The stresses that insist within your elements, within your bodies, and resorting to constitutive laws, you get the deformations. Now, passing from deformations to displacements, which is the final step, or rotation or whatever, you have to perform an integration. Okay, so when you perform an integration, you have to impose what? The so-called compatibility conditions that you have already seen in structural courses already. Okay, this compatibility condition that you take into account when getting from basically the loads, the stress state of your structure, and then the deformation, then eventually to the displacement or rotations, are enforced exactly to make sure that there are no continuity issues in your body, so that the deformation, when integrated, give you a continuous field of displacement or rotations. Okay? Okay. This characteristic is one of the main points that has to be satisfied when taking into account convergence for finite elements. Okay? So this is the general frame. Another main point, okay, but this is not enough. Another main point to grant convergence is the capability to represent correctly a state of constant stress in your body. Okay? Why is it so? Because a state of constant stress basically is equal to a constant value of the elastic energy in the body. Okay, so if the state of stress is constant, the elastic energy associated to the state of stress must be constant. A particular case of this study is the case in which the elastic energy, or if you want, the state of stress, is basically the null stress, so there is no internal stress at all, okay? Which correspond to which kind of motion, which we have seen, the kind of motion in which there is no basically deformation, rigid motion. So one of the points that has to be satisfied in order to grant convergence is the capability to correctly represent rigid motion in terms of energy content, okay, of your system. Meaning that if I take into account, I want to represent with my finite element approach a rigid motion, I have to see that there is no accumulation or variation of elastic energy. Elastic energy, you know, that is a quantity which can always be defined, but a constant, okay? So you actually always define differentials in the elastic energy. In particular, you can say that if this constant is 0, it has to stay 0 during a rigid motion. And this is what we are going to see today. If with this two-element formulation that we have prepared, the 2D isoparametric element and the 1D non-isoparametric element, within the absolute nodal formulation, we have these two aspects respected. Okay? So, Okay. All right, so let's check if this capability is actually fulfilled for the case of 2D isoparametric rectangular element. Let's write it like this. Okay. Okay, the first thing that we do is to define an energy, a strain energy. So let's say that we define so how is it defined? We typically call it U. It's the integral in general over the volume of the stresses, of the vector of the stresses that we have denoted in Voigt notation. So this is basically, it's a vector, it's not a matrix. Actually, it should be a tensor, in fact. Then we have a vector of the deformations, all of this being integrated over the volume. Now, since we are into 2D case, we can get out thickness, basically, and perform the integration over the area. And the stresses, as you can see, we have already known to do, is basically the product of the strain and the, in this case, it's elastic constant matrix. This is Hooke's law, so it's basically it's a linear approximation of the constitutive law. Okay, so basically this. Okay, all right. We define. Let me just let me just let me just turn the slide so that we can import a picture. It should be this one. Okay. So here you see the different, let's say, quantities which are involved in a general motion. So in this case, we also have deformation. Okay, we have a rigid motion plus deformation. In this, so what we are doing now is, writing the energy content associated to a general motion for 2D isoparametric rectangular element. So then we will apply this to the specific case of a rigid motion and see if the energy actually stays constant. That's what we're going to do. So we define deformation as, so we have epsilon ij is 1/2 of what? So you see here, let's write it with this. So this W here is the displacement, is the vector of the displacement induced by the deformation, by definition, okay? So here, adopting the linearized Lagrange deformation tensor, Green-Lagrange deformation tensor, this we will write it as Vj plus Wj, comma I over hat, where the comma is basically the partial differential operator. Okay? So this is the partial differential operator. And this is basically the linearized green Lagrange deformation tensor. So it means that we are in the hypothesis of small deformations, okay? Okay. So now, if you remember, for a single body, we had that the position of a point, general point within our body, was equal to r, capital R, plus small case r, okay? And in particular, this could be written as capital R plus A applied over R over bar. And this could be further, let's say, decomposing R plus A applied over R0 over bar plus U, okay? So this is basically what we have in the case of a single body. Now, let's imagine for the ease of simplicity, for the sake of easiness, that our body is composed of a single element. Okay, our body is has a single element only. So in this analogy, what do we have? That our local frame B1 and B2 translate to what? I1 and I2, which is the couple of vectors constituting the element frame, okay? Okay. Our position vector of a point expressed with respect to the local frame B1, B2 becomes what in this picture that you can see here? Huh? Exactly, it's X. So here we have X, and so here we have X over bar to be fair. Okay, and we have, of course, that R0 without much surprise becomes X0 over bar. And finally, our U over bar becomes our W over bar vector. Okay. Why do I do this? So this is basically, again, it's a simplifying hypothesis. In which you have a body composed of a single element. Okay. This means that we can rewrite this equation as such. Can I slide? Okay. We can rewrite P, which is always the position of a point of the body, equals to R plus A applied to X0 over bar plus W over bar. Okay? Okay. Now, since we have to get our deformation, because we need the deformation to calculate the energy, the strain energy, we need W, okay? So it means that W is A transposed P minus R minus X0 over bar, okay? Now, the matrix A, we have it, no? Because it's a typical rotation matrix in the 2D case. So it's cosinus of theta, sinus minus sinus of theta, sinus of theta, and cosinus of theta. Okay? Very well. Well, then R0, well, we have it. Okay? Sorry, R, we have it. X0 is given. The only thing that we don't have is P. Okay, so R is basically is R1 and R2. Okay. Yes, let's write it like this. R1 and R2, which are given. They are the position of the local frame, which is, in this case, the element frame. X0 also we have it. There will be X01 and X02. What does it mean that we have it? It means that it's up to us to choose them, no? The value. So it means that we need P, okay, to calculate okay, W. So how can we get P? Well, it's not that difficult because we know the formulation for the 2D isoparametric element. So far, everything has been pretty general. We have never actually taken into account the fact that we are dealing with a 2D isoparametric element, right? Everything is, everything that we have written here was pretty general. So now we take into account the fact that we are dealing with 2D isoparametric elements to get this P. And to do so, we do the following. We consider, in fact, in this case, a rigid motion. Okay. Yeah, should be this one. Okay. So here we have a rigid motion. Okay, so there is a rotation and translation. So here, as I was saying, we consider a rigid motion of the element. To do so, we have to determine the nodal quantities. So, for example, what are the values of E1? Okay. So E1, knowing that, as usual, this value here is basically is B. Okay. And this is B as well. This is B. And of course, here we have that these two quantities are C and C. And the angle there is theta. So E1, I want you to have it clear in mind that E1 is this quantity here. E1 is the position of the node 1, in particular the component along the direction given by x1. Okay, so this is E1. So how can we actually guess E1 from the picture? So E1, I would say it's R1. R1 is this one, right? So R1 is this one here. This is R1. Okay, it's the component along the axis x1 of the position of the origin of the element frame. Okay, that's R1. So basically, I would try to get this E1 as the difference between R1 and this quantity here, okay, which is left. So I would say that this is R1 minus what? Well, I would say that this quantity here is basically this quantity here times the cosinus of this angle here, which is this, because this is theta. So this is theta, and this as well is theta. Okay? So I would call this minus B minus C, the tangent of the angle theta, all multiplied by the cosinus of theta. Okay? So basically, C, if you write it like this, C, the tangent of theta, is this part here. Okay? Because this is C. Okay? C times the tangent of theta is basically this one. Then you remove from B this part, and you get this. Once you get this, you multiply times the cosinus of theta, and you get this part here. You remove this part here to R0, you get E1. Okay, so I think it's easy. Now you do the same thing, the same kind of reasoning, which I will spare to you, for all the nodes, and for all the directions, so 1 and 2. So that you get the vector of the nodal quantities E. Okay? So we can say that, oops, for all nodes, we get that E, which is E1 it's the following. And this is what we have just calculated, the first one, E1. Okay, this is what we have just seen. So the rest is pretty much the same, which I will write here just for the sake of completeness, so that you can verify and whatever, and check that we are actually saying the truth. Okay, so this is the vector E that you get, doing basically similar reasoning to the one that we have just performed. And so you eventually can write, as you remember, that E is equal to psi over bar to the minus 1 over A. This is what we basically found out. And eventually, if you remember, P is equal to psi operated over A. Okay, where this psi is the vector. Okay, someone made me notice this, and it is in fact true. So I should have written it with an overhead, because a couple of lectures ago, we have introduced the FEM shape functions and differentiated them from the shape function of the general restricted approach formulation, because we denoted them with the overhead, and we call them head functions. Okay, it is true. Okay, why I actually dropped the overhead sign? Because basically the FEM formulation is the typical restricted formulation that is adopted in practice. So many times you can see them integrated by this, but we can actually, either keep it or drop it. I would drop it just for the sake of notation, but given that it's clear that this psi is the psi of the FEM formulation. Okay. All right. So this is the shape matrix of 2D isoparam rectangular elements that we have. Okay. So this we have it. This one also we have it. So we can get P that we lacked. Okay. Eventually, if you do this calculation, your P becomes over E. It's of course a two-dimensional vector because there are two basically coordinates in our space, or our space is of order 2 if you want. And if you do the calculation, what you get eventually is this. Okay, this is your P. In case of what? This is the displacement field of every general point within your 2D element in case of a rigid motion, for rigid motion only. In fact, as you can see here, there are no coordinates associated to deformation. Okay. All right. So at this point, let's actually calculate our W. No. So W becomes 1 and 2, of course, as usual. It's A transposed. If you go and check. Applied over P minus r. So we can write it like this. Okay, minus x1 over bar, x2 over bar. Here, basically, this is P minus R. So, how much is it? Well, if you go and check, it's the null vector. What does it mean? It means that when I take into account a displacement field associated to a generic rigid motion, I get no displacement induced by deformation, which is what should actually happen. And therefore, we don't need to check, I guess. So the strain energy is equal to 0. And this is, of course, the correct behavior. So we say that to D is a parametric rectangular element possess all the requirements to converge or to guarantee convergence. Okay, so it's okay to use them, okay, within this formulation. Now, let's do the same check for the 1D non-isoparametric beam element, okay? So, I'm going to get the verification. If you want, of the energetic consistency. For the 1D beam non-isoparametric beam element. Okay. Again, we consider rigid motion. So we have basically r and theta as variable. And okay, I will spare you all the part that we have gone through already. So let's go directly to the definition of our nodal quantities, which in this case are 6, if you remember, no? If you remember. Okay, we have 6 nodal quantities: E1, E2, E3, E4, E5, and E6. So now it's actually easier. So you tell me, what are these nodal quantities? E1 is the position, is the, let's say, the component along x1 of the position of the element frame, of the origin of the element frame. So what is it? Exactly, it's R1. right? I guess that's pretty obvious. Then we get E2 is equal to R2. E3, which is the rotation of the frame. It's actually, if you remember, the angle between the tangent to the element at that point and the axis x1. So now, basically, there is a rigid motion. So it's basically this angle is the angle between I1 and x1, right? So it's theta. Okay. And then what else? This is R1 plus, say this is the length of this is, let's say it's L. So what's the position of the node number 2 with respect to x1? All right. And then R2 plus L sinus of theta, and then we get theta as well, right? Now, in the hypothesis of small rotations, this becomes like this. Okay. So we linearize basically the trigonometric function. Then, with this in mind, we would say we act as we just did for the 2D element, and eventually we get P, which is equal to psi operating over E. And in this case, you get R1 plus x10 and R2 plus x10 theta. Okay, so again, this is the shape functions of 1D non-iso okay, so the ones that we have already defined. If we proceed now and try to get W, so our W now, again, is A applied over P minus R minus x0 over bar. Now A, which is the cosinus of theta minus sinus of theta, sinus of theta, and cosinus of theta, with the hypothesis of small rotation, becomes 1 minus theta, theta 1. Okay? Again. In fact, when we perform this linearization, we have to check one thing which is important. So it must hold that A applied over A transposed must be the identity. Because when so what I'm saying is that when I linearize this rotation matrix, I have to always make sure that the property of orthogonality is maintained, okay? So I must check orthogonality. And let's check it actually. So if I do A applied over A transposed, what I get is 1 minus theta, theta and 1 applied over 1 theta minus theta and 1, which is 1 plus theta squared, 0, 0, 1 plus theta squared, which is not, of course, sorry, the identity matrix. Therefore, I define, it's not that I define, I actually correct the linearization operation, and I say that A is actually 1 over the square root of 1 plus theta squared applied over 1 minus theta, theta, and 1. Okay, so that now A applied over A transposed is actually the identity matrix. Huh? Okay. Now let's actually finally determine W. So we have now the W, which again has two components, W1 overhead, overbar, and W2 overbar, are 1 over the square root of 1 plus theta squared. Applied over 1 minus theta, theta and 1. Now I basically have to subtract. I have to subtract R1 and R2 to this. Okay, so I'm left with x1 overbar and x1 overbar theta. So I write it. Minus. So what is x10 vector in this case? So this is a 1D case, if you remember. So what is the initial position of a point? Well, typically it is always on the line, on the direction described by I1, right? So it has basically 0 as second coordinate because it has to stay on the axis, right? Before, prior to the formation. So it's like this. Okay? And so eventually this amounts to x10 if you do the count, which multiplies the square root of 1 plus theta, squared, minus 1, and 0. Okay? So this is W. Okay, it's already suspicious that the vector of the displacement induced by deformation in a rigid motion is non-zero. But okay, let's check. Let's check the energy. Now, how do we define the energy? So let's calculate the energy. associated to rigid motion. Okay, for 1D beam element. So our U is typically what? 1 over 2. The integral, this is actually we have already encountered. From 0 to L of what? Of the axial rigidity, EI, the derivative of W1 over bar with respect to the X10 over bar squared. This is basically the axial deformation. This is the energy strain associated to axial deformation. Plus the second order, the derivative, the transverse deformation, always with respect to X10 squared. All this being multiplied, of course, times the X10 over bar. If you do this, you get that dW1 over bar, the X10, and the W2 respect to 10 are. So this one is 0. If you go and check W, because it's basically automatically 0, you see here. Our W here, W2 is 0 automatically. So the second order derivative that we have here is 0. Okay? But this term here, which is associated to the first order derivative of W, well, I'm afraid it's not. If you do the derivative, you get this. Which is different from 0. And therefore, U is different from 0, or is non-constant. Actually, if you do it, actually it's like this. If you do the calculation. Which is, of course, again, different from 0, as I was saying. So it means that the 1D non-isoparametric beam element is not capable to correctly represent, from an energetic point of view, a rigid motion, because it associates with a rigid motion a strain energy which is not 0. Okay. So it does not work in absolute nodal formulation. So what do we do now? We just trash 1D beam element? Of course not, even because we already know that these kind of elements are typically used. So there must be some solution to this. And the solution is exactly to use the same element type, but within another formulation. Formulation in which the nodal quantities are not referred to the inertial frame, but to the element frame itself. Okay? this formulation is the floating frame formulation. So the floating frame formulation is a formulation which has been exactly introduced to make possible the utilization of non-isoparametric elements, so those ones which are associated with the use of rotations as nodal coordinates, without, meeting issues associated to issues which are then issues of convergence associated to energetic misrepresentation of the energy content of the element. So what is the, again, fundamental hypothesis associated with this formulation? Nodal coordinates expressed with respect to the element frame. Okay? So let's actually reconsider. Let's derive the psi in this case. So again, let's take into account the previous picture, which is still good. So say we have this one, right? So typically the first step that we do is to assume the physics of the element. Okay? And we always assume, as we have done so far. You see now, I'm not actually writing P1 as we did, but X over bar 1. A0 plus A1 X10. So please again check that this is not P1, okay? And then X2 over bar is A2 plus A3 X10 plus A4 X10 squared plus A fifth X10 to the third. So this is, again, Euler beam model. Okay, so we make the same choice. So why are we doing all of this? Because now we are trying to develop another formulation for this element type so that we can use it, without causing issues in convergence. So we will now try to get this psi, re-verify the energetic representation in presence of a rigid motion, and in this case we will see that it works. Okay? So this is the logic that we are following. So in matrix form, x over bar is equal to phi applied over A. So this is the first, let's say, representation that we need. With this phi matrix, which is equal to, well, exactly the one that we have already seen for the nodal formulation. Why is it the same? Well, because the functional dependence is the same. We always have chosen the same Euler beam model, okay? So the parameterization is the same. That's why we get the same matrix here as before. Okay. Again, we impose now the equality condition at nodes. Can I slide? So step 2, we impose equality conditions at the nodes. And so we have that x1 over bar of 0 must be E1 over bar. Then we get the x2 0 must be equal to E2 over bar. And x2 at 0 prime, which is the tangent, again, of alpha at 0, which is pretty much alpha at 0, must be equal to E3 over bar. Again, here we have small rotation hypothesis. And the same goes for the second node. No? So this is first node, and this is the second node. So we have x1 over bar at L must be equal to E4, and x2 over bar at L must be equal to E5 over bar, and x2 over bar prime at L, which is equal to the tangent of alpha at L, is pretty much equal to alpha at L, must be equal to E6. Okay, and again, small rotation hypothesis holds. Remember that alpha is exactly, the angle that we have defined before. So in matrix form again, get E over bar, and please note the over bar thing. Okay. Let's actually. I made a mistake here. Let me see, because this is not the. You see, this is not the right picture, because if you check here, E1, E2, E3, in fact, so they are all oriented along the inertial directions. While now we have said that the nodal quality should be aligned with respect to the element frame. So this is not the correct picture. Not sure if I have the correct one here. Otherwise, I can correct it. Let's see. It's not important. I don't think I have them. No. So let's see if we can do something about this. I'm not sure. Well, we should have that. We'll correct them with the red color. So this is E2, E2 overbar. And here we should have E1 overbar. Okay, so that basically this doesn't exist, and this as well. Okay, so these are E1 and E2, and the same goes for E4 and E5. Okay. So basically you get this is E5, if I'm not mistaken, overbar. No, this is I4, exactly. Okay. Theta? Sì, esattamente. Okay, so this is what we are actually dealing with now. And so that's why we have an overbar here, because it's basically the same quantity but described with respect to another frame. And so this becomes C overbar applied over A with this C overbar that we have already encountered. I will write it just for the sake of completeness, but bear with me that, of course, this is kind of boring. Show you write it like this. That's it, actually. Okay. And therefore, we get that our X overbar, which is phi over A, and then A we have just got, which is basically C overbar to the minus 1. And this is exactly our phi applied over E. Okay. So this, as usual, is our matrix. let me just write for you this psi matrix. Not sure if I have enough space here. I'll try. Is 1 minus zeta and 0. Then you get 1 minus 3 zeta squared plus 2 zeta to the third. And above you have 0. Then you have L applied over xi minus 2 xi, this is zeta squared plus zeta to the third. And above you get still 0. Then you get zeta here and 0. You get 0, 3 zeta squared minus 2 zeta to the third. And then 0 again on top. And L multiplying zeta to the third minus zeta to the second. Okay. If you don't see it, I can repeat it. If it's too small. I just wanted you all to get all of the information on the element on the same slide. That's it. Okay, so now we have determined psi. Let's again check the energetic misrepresentation, if it's present or not. And if it's not, then it means that this formulation will actually be able to use this kind of elements with all the pros that they have, like the use of nodal coordinates at the nodes, which are very useful, for example, to implement boundary constraints, for example, hinges and so on, or connections between links. So we now consider a rigid motion. So again, we have to determine all the vectors of the nodal coordinates. Again, here we should use the correct picture, which I don't have, so we have to do what we have. So this means that I'll have to correct this. So just give me a second. Okay, so we get this one. Oh, this is E1 over bar. We have E2 over bar, and then again E3 over bar. And here we get the same, so we get E4, E5, and E6. Okay, that's it. So let's actually now try to derive these quantities in terms of, again, a rotation theta and a translation r. So what's the content? So what's the coordinate? What's the value of E1 over bar? So the position, the coordinate along I1 of the position of the first node given with respect to the element coordinate I1, I2. Exactly. How about E2 over bar? E3? Exactly. Remember that E3 will not be 0 when, for example, you have a deformation. And then the tangent to the mean axis with respect to the element frame is not parallel. Okay? So it's 0. Well, how about E3 over bar? Any guess? No, it's not L cosinus of t. It's L. It's just L. And then E5, 0. E6, 0 again. So as you can see, it's super simple. That's to say, when you get x applied over E, you eventually get what? X1, 0, and 0. So you apply this one that we have just determined to E, which is this vector, the only surviving terms of these two. Okay? It follows that W, which is A transposed over, in this case, P minus R, this is what we get before, minus X0 over bar. But this one here, what is it? This quantity here, in the single element body analogy that we have done. Go and check. Actually, sorry, let me show it to you right now. Oops. So here we have that W is something minus X0. Go and check this. W, here you have that X over bar is basically X over bar 0 plus W. You see, you start from here, you go along X1, 0, then you add W, and you basically have done the part of X1. This, by definition, X over bar is X0 over bar plus W. So what is it, this one here? It's X over bar. Okay? So that you get basically that X over bar is X0 over bar plus W if you invert the equation. Is it okay? It's basically from definition. How much is this? Well, this one we already got. X0 is the same as before. And the result is 0. Okay. So what does it mean? It means that in this case, the exact same element type, but used within another formulation, which make reference to another frame, associate 0 displacement induced by deformation as a consequence of a rigid motion, as it should be. So therefore, U, I don't rewrite U. U is the same as before, huh? The energetic. Okay. So basically, this means, again, to recap, that in this case, the element type, the same element type, associate 0 strain energy to rigid motion. And therefore, it fulfills one of the two conditions required to get convergence properties, which is, of course, fundamental for finite element applications. And that's why these kind of elements are used in codes, as in atoms as well. Okay. So the only consideration which is left here to do is, so the absolute nodal formulation is trash. Why do we use it? Well, remember that to get here, we have done an assumption of small rotation angles. So it means, and we will see that, in fact, the use of 1D beam element, non-isoparametric element, comes at the cost of small rotation induced by the deformation. We will see it. We saw it already here because we have made this hypothesis, but we will confirm this hypothesis later on. Okay, it means, so have this clear in mind. Theta is the rotation associated to rigid motion. Alpha is the rotation associated to deformation. Alpha has to be small, okay, in this application, and we will see it also later on. When we use instead 2D isoparametric elements within the absolute nodal formulation, we made no assumption on deformation, or small deformations, on small rotation, or so on. So it means that the advantage of the absolute nodal formulation is typically that it can take into account non-linear, basically, or in any case, large deformations. So you can have large rotation induced by a large translation induced by the rigid part of your motion. And this is always true. But then when it comes down to deformation, the absolute nodal formulation is able to deliver good results, also when you take into account large deformations, given the fact that you use the appropriate elements, so not 1D elements. When you use the floating formulation, you can use 1D element, beam element, which you can't use in the absolute formulation, but you have to pay attention because this is only working in the case of small deformation, not small rotation in general. So you have a beam, it can rotate wherever as long as it does it rigidly, but then when it has to deform, pay attention. Otherwise you have convergence issues. Okay, and this is all for today.